everybody. Let's solve today the problem invert binary tree. I hope you know what a binary tree is. So a binary tree is something where a parent node has its two corresponding child node, the left child and the right child. So it has exactly 0 or 2 child nodes. Means exactly 0 2 child nodes per parent node. So this is the definition of a binary tree. Now they have asked us to invert the binary tree. That means if I take this example 2, 1 and 3, after operations it should look like 2, 3 and 1. I'm inverting and we have to, the main thing in here is that we have to change the links. We do not have to change the values. We do not change the values of these individual nodes, but we actually change the links. So if I take this, so 2, then 1, okay, let me draw here. So if I have something like this 2, 1 and 3, and if I change the color of this, so let me draw like this 2, and then let me take this color 3. So after operations, my binary tree should look something like this 3, like this. So we are actually changing the links. We are actually changing the links. That's how it works. Oh, sorry, one second. This will be 1 and 3. Just a small mistake. This will be 1 and 3, like this. Actually, you see this brown is the left pointer, and this green is the right pointer. So this will look something like this 2, 3, 1. This will look something like this. That is exactly correct. But we are not changing the values, we are changing the links. That's why I've drawn like this to make you understand that we are changing the links, we are not changing the values. Now let's see how we will solve this. So let us take the example 1 which they have given us 4, 2, 7, 1, 3, 6, and then 9. Let's draw this 4, 2, 7, and then with another color, let's say green, the right pointers. Okay, this is, now let's see how we will go on solving this. So we will use our data our depth first search, that is DFS algorithm, to go through the tree. Okay, so I will start from root. I will go here, I will go here. Here I will check whether this has a left and right nodes. So I will take left equals to null, right equals to null, and I will interchange these two links. Since all these have null as their child nodes, so there is no noticeable change in these things. Let us go above. Let us go a step above and see what happens. When we are here, when we are at this node, the left is 1, the right is 3. Right. Again, I am telling you, we are not changing the values, we are changing only the links. Here, what we will do is we will just change the links. We will just change the links. So this becomes 3 and this becomes 1. We have changed the links. Green is actually the right pointer and brown is actually, sorry, and brown is actually the left pointer, right? You can see here we have actually changed it, right? We have actually changed these things. It is not seemingly like that, but we have changed it. Here also, when we are at 7, the left is 6, right is 9. We just interchange them. We just swap them. Okay. So left becomes this one, and right becomes this one. Again, when we are at 4, at the root node, in here, the left pointer is pointing at 7 now. If you see very carefully, the left pointer is at 2. Okay, brown is left. So left pointer is at 2. 7 is pointing to 4 is pointing to 2. So left becomes 2 and right becomes 7. Here again, we interchange it. So we are changing the links only. We are changing the links only. So this becomes brown and this becomes green. Okay. Now when we redraw this tree, how should it look like? See here. Now when we redraw this tree, okay, I hope you can see it. Now when we redraw this tree, it should look something like 4, left pointer is 7, right pointer is 2. 7's left pointer, that is brown, is 9. 7's right pointer is 6. 2's left pointer is this one, 3. And 2's right pointer is this one, 1. We have inevitably changed the links, and thereby we have got to the answer. We have achieved the answer. We have changed the links and we have achieved the answer. So this is a simple way to do this. Basically, we are changing the links. That is the main thing. Change the links, not values. The individual nodes value should not be changed. We just change the links of them and we got the answer. Okay. Now let's now see how we can put this in Java. Since we are using a depth first search algorithm, so let's write the base case. If root equals to null, return null. That is when we are reaching a child node which has we reach a parent node which has no child nodes. That is, both of the child nodes are null. Now we will take two variables, that is tree node left and tree node right. Tree node left equals to invert tree. Here we are implementing the DFS algorithm, root.left. Right equals to invert root.right. Okay, here what we do is we are going to the end, right? Let me show you once more. In this case, what we are doing is that we are here and we are implementing DFS, so we are going right at this node. We are going at right this node. Okay, we are going at right this node. We are at 1. Now we interchange these two. Now we interchange. It has null, it has null. So in this case, it does not change anything, but actually we are doing something like this in the first step. So let's change this. Interchange. How we will interchange it? This is a very good thing. So root dot left equals to right. Simple. Root dot right equals to left. Just as simple as that. And then we return root. Just like that. Let's try to run it. Okay, it is successful. Let's try to submit it. Before submitting it, let's see once more what this code is doing. You see here, root dot left equals to right and root dot right equals to left. So suppose we are at 7. We are at 7. Then left equals to 6 and right equals to 9. So what we do is we interchange these two links, right? This was pointing previous to here and previous to here. So root dot left equals to right. What is right? 9. Root dot left means this goes here now. And root dot right equals to left. So this pointer which was originally here, this now points to this node. That's how we interchange it. And then we return the root. Let's try to submit it. Okay, that's correct. Okay, thank you.